What's going on, my friends? Welcome back. Hope you're all doing really well and surviving this, whatever this is, this existence. Can be brutal, so hang in there. If you're going through rough times, especially if you're studying physics, it can be tough. And just hope you guys are doing alright. Today we're going to watch some more physics, more science. Check out CalVPN if you haven't already. I'm going to briefly tell you about my other thing that I'm doing. It's like, so if you haven't been watching lately, I'm creating 2 startups. One of which I've already talked about. Go watch the other videos. CalVPN first, quantum-proof VPN. Check it out in the bio. And I'm also creating something that might appeal to you guys a bit more. It is a Squarespace for YouTube creators. So maybe I won't say too much more right now, but if you want to create a YouTube channel, this is going to be something you want. It's going to help people do what they want. So I'm looking forward to telling you more. Stay tuned. That one will be developed rapidly. I'll have much more to say within the next week about that, and I can show you some stuff. Anyway, let's get on with the video. Let's go watch something. And we are checking out the largest black hole in the universe size comparison. So let's do this.
The largest things in the universe are black holes. In contrast...
That's, I don't think you can say any such thing with such certainty, because as far as we can tell, but again, I don't think it's correct to say things. Maybe if you said objects, it would be more correct, but I think the largest things, the most massive things in our universe, as far as we can tell, are dark matter halos. Maybe the cosmic web itself, which is the large scale structure of dark matter.
To things like planets or stars, they have no physical size limit and can literally grow endlessly. Although in reality, specific things need to happen to create different kinds of black holes, from really tiny ones to the largest single things in the universe.
Like I mentioned in the last video I did on him, the Kugelblitz is another kind of way to make a black hole. But if you want to know about that, go watch that first one.
So how do black holes grow? And how large is the largest of them all?
It's pretty big. And I'll let him explain how they grow, and then I'll chip in. It's a bit of mystery involved.
This video will not discuss how black holes work or how they form, since we've looked at that in detail in our black hole and neutron star series. You can check them out afterwards.
Will do.
For now, we're interested in finding the largest thing in the universe. Let's start really small. Primordial black holes. The smallest kind of black holes may or may not exist. If they do, they're probably the oldest objects in the universe, older even than atoms. They would have formed...
Oldest objects in the universe? Absolutely not. That is not true. There'll be, a lot of things older, but so let's not get into that. I did want to say, though, you might have heard how there could be a planet 9 in our solar system, well beyond Pluto. Yes, I know, Pluto isn't classed as a planet anymore, but there could be something well beyond Pluto that has, a large mass. And some people think it's potentially a planet, but they're confused as to why we haven't, potentially seen it. But some people think it could be a primordial black hole, and it would have about, I think it's like 9 Earth masses, 7 to 9 Earth masses, and it would be the size of a baseball. Size of a baseball with 9 Earth masses. Crazy.
Formed just after the Big Bang, when the universe was so dense with violent energy that any tiny pocket that was just slightly more dense than its neighbors could produce a black hole.
Exactly.
The smallest primordial black hole that could still be around would be 8 trillion kilograms or so, the mass of a big mountain. And yet they would be no bigger than a proton. A primordial black hole with the mass of Earth would barely be larger than a coin. This makes them very hard. He
missed a golden opportunity right there, because yes, if you squash the Earth down to the size of a nut, you'd get a black hole. It's Schwarzschild radius. If you go beyond that, that's what creates a black hole, theoretically. And so yeah, this guy could have used the nut. That's his name, right? In a nutshell. Earth in a nut. Missed the golden opportunity.
To find, so we haven't actually observed any yet. If they exist, they may even be the mysterious dark matter.
He's saying if they exist, but I think he should be saying they're theoretical. Yeah, but they could be out there for sure. And like he's saying, could be dark matter, but all black holes could be, other black holes could be the dark matter as well. So
that holds galaxies together. Let's move on to the kinds
An
of
interesting question for you out there. Do black holes, do they eat dark matter? Let me know down under.
black holes that we know for sure are out there. Stellar black holes.
Okay, but even stellar black holes, you know, like, are they really out there? Because black holes might not be what we think they are. And you might be like, but Dylan, we've got pictures of them. But that doesn't mean, you know, they're these holes in space-time. It could just be something dense enough to, you know, swallow light. Doesn't mean there's a singularity inside. It could be just something extremely dense. And that would be sad because, you know, hopefully they are way more mysterious than that. And, you know, if string theory is correct, there are these even weirder things again called fuzzballs. Yes, fuzzballs. The most violent things in the universe in string theory are potentially called fuzzballs, which is like, you know, the string theory, right? So you got these large strings and they're all like mixed up together. And I think from memory, they have a solid surface, but I think, anyway, we'll have to go look into that. I haven't read about those for a while. Good name for a pet.
To make a black hole, we need to compress enough matter so that it collapses into itself. After that, the more mass we throw at it, the larger it becomes. In today's universe, only the most violent cosmic events can create the necessary conditions, such as the merger of neutron stars or when the core of a very massive star collapses in a supernova.
Hell yeah.
To have a unit to work with here, we'll use the mass of our Sun, about 2 million trillion kilograms.
It's a big boy.
The smallest known black hole has 2.7 times the mass of the Sun, which works out as a sphere around 16 kilometers in diameter, large enough to cover Paris.
Yes, the size of a small town. If you crush the Sun down to the size of a small town, black hole.
Another lightweight black hole is the companion to the V723 Mon red giant star. This star is 24 times larger than our Sun, 30 million kilometers in diameter. And yet, it's thrown around by a tiny black hole just 17.2 kilometers wide. This tiny thing bullying the star is so much smaller that we can barely even show them in comparison.
Those black holes got that small person syndrome to, you know, exaggerated degree. But I just wanted to chip in and say here, I actually named my cat after a black hole. He's named Cygnus. It's named after the first ever discovered black hole, Cygnus X1. And there's a funny story behind it. Stephen Hawking and Kip Thorne had a bet that it either was or wasn't a black hole, and the wager was like a year subscription to Penthouse magazine or something back then, which is like Playboy. Classic.
One of the largest known stellar black holes is M33X7. It currently spends its time eating a 70 solar mass blue giant bit by bit.
Wait.
As all that stolen matter circles towards the black hole, like water going down a drain, friction heats it up to temperatures high enough to shine 500,000 times brighter than our Sun. And yet, X7 is only 15.65 solar masses and 92 kilometers wide, just big enough to cast a shadow on Corsica. To grow, one of the largest known stellar black holes is M33X7. It currently spends its time eating a 70 solar mass blue giant bit by bit. As all that stolen matter circles towards the black hole, like water going down a drain, friction heats it up to temperatures high enough to shine 500,000 times brighter than our Sun. And yet, X7 is only 15.65 solar masses and 92 kilometers wide, just big enough to cast a shadow on Corsica.
Where the hell
to
is
grow
Corsica?
Much larger, black holes have to either devour a lot of stars, or better, merge with one another. The instruments that make it possible to detect these mergers are very new, so we're currently discovering a lot of exciting things. Like two massive black holes that we detected in a galaxy 17 billion light-years away. As they spun around each other violently, they released more energy in the form of gravitational waves than the combined light from all the stars in the Milky Way in 4,400 years.
Man.
The new black hole they formed is about the size of Germany and is 142.
I liked how in his little animation it was like warping the actual fabric of space-time as well. That's what happens. It's crazy. They drag around the fabric of the universe itself. Nuts.
2 solar masses. And here we hit a curious gap in scale. There are lots of black holes up to 150 solar masses, and then there's nothing for a long time. Until we suddenly hit black holes that are millions of times more massive. Which is a bit confusing because we had this idea that black holes are consistently growing and growing. But for the most massive black holes, this process is not fast enough to explain their existence today. The universe is simply not old enough for these
That curious gap is probably, we just haven't found them yet. We think there's something like 100 million black holes in the Milky Way alone. They're everywhere. I hope that doesn't scare you, though. But there was something else I was going to say. That, yeah, these supermassive black holes are curious things because we really don't understand how they got so big and how they got so big so quickly, because they got big very quickly. We'll come back to this. I'm sure he's going to touch on it.
Massive black holes to have formed by meeting stars and merging with each other. Something else must have happened. To explain how we got the largest black holes...
Yeah, we think everything in the universe grows hierarchically. You know, from you get two things and they merge and becomes bigger, right? Everything's gravitationally bound.
In the universe, we might need the largest stars that ever existed. Quasi-stars. To get a sense of scale, we can compare them to the largest stars that exist today. Our sun is like a grain of sand next to them.
They're not normal stars. They're really cool.
Don't know if quasi-stars actually existed, but they're an interesting concept when it comes to supercharging black hole development. The idea is that the matter in the early universe was so dense that quasi-stars could grow to thousands of times the mass of our sun. The cores of these stars might have been crushed by their own weight so much to actually collapse into black holes while the star was still forming. In contrast to stars today that would destroy themselves in the process, inside quasi-stars, a deadly balance could emerge. Gravity pressed the supermassive star together, feeding the black hole and heating the material falling in to such a degree that the radiation pressure kept the star stable. So these quickly growing black holes might have been able to consume the quasi-star for millions of years and grow far bigger than any modern stellar black hole. Black holes several thousand times the mass of the sun and wider than the entire Earth. These black holes might have become the seeds for supermassive black holes.
Yep. And, you know, in that early universe, obviously everything was a lot more dense. The universe was smaller, things were closer together. There was just, you know, a lot of gas that was closer together. And so you could imagine that, you know, through gravitational, you know, everything coming together, some stuff might have just collapsed in on itself and created these huge black holes because there was so much, you know, so close together. Now everything's a lot bigger. The universe is expanding. It's accelerating in its expansion. The black holes have probably consumed a lot of that early stuff. Not a lot, but some of it at least, you know, because it's important to recognize that in galaxies, the supermassive black holes make up like a really, really small amount of the mass. It's crazy. Can't remember the exact, it might have been like 0.1% or something, but anyway.
So now we arrive at the kings of our universe, the largest single bodies in existence.
There is a bigger,
the centers of most galaxies contain a supermassive black hole, and they are monstrous. In the Milky Way, we have Sagittarius A star, a supermassive black hole with about 4 million solar masses that is calm and collected.
So I think it's a little bit inaccurate to show them differently like this. Like, look, it looks different to the last one, but this big boy would also have an accretion disk and look just like the last one. And we just took an image of it as well, you know.
Accretion disk does its thing. We know it sits there because we can see a number of stars being thrown around by a seemingly empty spot. And despite its incredible mass...
A brilliant woman won a Nobel Prize in Physics for basically, you know, looking at how all the stars at the center of our galaxy, they're all like moving around in this complex pattern, and there must be some huge amount of mass at the middle of it. And supermassive black hole in the middle of the Milky Way. I can't think of a name right now, but yeah, it's a cool little thing.
Its radius is still only 17 times our sun. Smaller than most giant stars, but millions of times more massive. Because supermassive black holes are so massive and located at the center of galaxies, many people imagine them as being a bit like the sun in the solar system. An anchor that glues everything else together and forces it into an orbit. But this is a misconception. While the Sun makes up 99.86% of all the mass in the solar system, supermassive black holes usually only have 0.001% of the mass of their
that's what I was saying. I was a little bit off. It was 0.001, not 0.1.
Galaxy.
Crazy.
The billions of stars in galaxies are not gravitationally bound to them. Instead, it's the gravitational effect of dark matter which holds them together.
Okay.
Many supermassive black holes
there's a lot of dark matter in
especially
galaxies that are holding a lot of them together because otherwise they would just kind of fly apart. Anyway.
When they're feeding on the clouds of mass in their galaxy. The one at the center of the BL Lacerti galaxy is devouring so much material that it produces jets of plasma accelerated to nearly the speed of light. If Earth were orbiting this huge body, it would seem 115 times larger than our Sun in the sky, and we'd be burnt to a crisp in seconds by its glowing hot accretion disk. At this point, black holes become so large that stars seem ridiculously tiny compared to them. The galaxy Cygnus A has a supermassive black hole with 2.5 billion solar masses and 14.7 billion kilometers wide, which would mean that if it took the place of our Sun, it would swallow all the planets and stretch halfway to the edge of our solar system. It's devouring so much mass and material that it churns its disk into a kind of magnetic funnel, spewing gas out, making tremendous radio lobes towering over the galaxy 500,000 light-years in diameter. That's 2.5 Milky Ways wide. Another pretty large supermassive black hole sits in the galaxy Messier 87. It has 6.5 billion solar masses and was the first black hole we got an actual photo of, or rather, of the glowing gas around the edge of a menacing shadow. This sphere of darkness is so large that it covers our entire solar system. And yet, there is a scale even above these kinds of objects. Ultramassive black holes. Now we reach the most massive black holes, perhaps the largest single bodies that will ever exist. These black holes have eaten so much that they've grown to tens of billions of solar masses, their gravity the engine for a quasar, an accretion disk shining brighter than thousands of galaxies full of stars.
Unbelievable.
So massive that they deserve a title of their own. Ultramassive black holes.
These are the ones that our theoretical models, our simulations of the universe of cosmology really struggle to... we can't really find them. Black holes just won't grow this big. And so there's some stuff we're missing, whether it's, some mechanisms we're missing or, the baryonic physics, the physics of the stuff, we can see. Where we could have some things wrong, Like I said, I think earlier, our understanding of gravity could be wrong. Dark matter might not even be real. It could be something like modified Newtonian mechanics. Who knows? It seems like there's some problems. And like the dark matter stuff, it might not just be made of one kind of thing. There could be like an entirely new standard model of different dark matter stuff, or even multiple, like, who knows?
Holes. The ultramassive black hole at the center of galaxy OJ287 is 18 billion solar masses. It's so big that it has a supermassive black hole nearly 40 times larger than Sagittarius A star orbiting it.
And like I said, actually I'm not sure if I said it earlier, but these quasars only exist in the early universe. We don't see them anymore around us. There's lots of dead galaxies around us now where star formation has stopped. They're not really forming any new stars. And the quasars, or the supermassive black holes, aren't igniting their accretion disks like they did in the early universe. And I just wanted to add these black holes that he's talking about. We find them in the very early universe. It's like, how did they get so big so quickly? It just doesn't seem like there's enough time for them to grow to this size hierarchically. There must be other mechanisms. Just like I was saying, the clumping together really quickly and collapse of stuff could potentially explain it, but in our models, it still doesn't. So it is a mystery. So if you're interested in this stuff, you should go get involved, help figure it out. And, even the galaxies at this early time, they got so big so quickly, and then they started quenching, which is what we call like a kind of like a dead galaxy, essentially. we see quiescent galaxies in the early universe, and we really can't explain it. But anyway, let's keep going.
This thing defies imagination and is really hard to compare to anything. It can comfortably fit 3 solar systems side by side inside of it. Let's end this insane competition and get to the King of Kings. Ton 618, a black hole that we can observe consuming galaxies worth of matter, is shining with the brightness of 100 trillion stars, visible from 18 billion light years away. It has an incredible 66 billion solar masses, a black hole so large that it would take light a week to reach the singularity after crossing the event horizon.
Crazy.
About 11 solar systems could sit inside of it, side by side.
Wow.
It may very well be the largest single body in the universe.
I think it has like 40 billion solar masses, this one.
But in reality, it's probably even larger. Since Ton 618 is so far away, we only see what it looked like 10 billion years ago. In any case, black holes are
only like 3 and a bit, billion years after the Big Bang. It's crazy.
Scary and mysterious and gigantic. They'll be here after everything else dies and growing larger and larger. Okay, now let's do the trip again. From the smallest possible black hole all the way up to the largest.
Yeah, like I said, they probably should all look fairly similar. Wow. Okay. There's the Earth. And we're already beyond what we can comprehend. Sagittarius A, the center of our Milky Way. Very big now. There's the largest star. Cygnus A. There's the first image. Getting really big now. Nice. Beautiful.
Try something new today. We can call it Behind the Lies, a short behind-the-scenes bit about the necessary inaccuracies in this video, because it's not really actually possible to rank black holes like trading cards. How so? Well, while we've catalogued millions of stars, we really only have good data on a couple of dozen black holes. That's because black hole gazing wasn't
I'm glad he's going into this. This is really great.
really a thing until 50 years ago, and technically still isn't because we can't see black holes. We can only derive their properties from studying their gravitational effects on the matter around them, like the orbit of stars that come close to them. This effect depends on the mass of the black hole, which we can approximate.
Now we have the images as well, so some direct evidence. But yeah, he's exactly correct. These things are still theoretical. The way they work, we still don't understand.
Level with Kepler's laws. But this comes with huge uncertainties and error bars. Then we have to convert mass to size next, which brings new uncertainties. For example, we calculated the radius from the mass using the Schwarzschild equation, which for the sake of simplicity assumes black holes are perfectly round and don't spin, a kind of black hole that doesn't really exist. The reality is that physics on these scales is a bit fuzzy. So some of the black holes we talked about here may be way smaller or way bigger. We just don't know for sure. We shimmied around this problem by comparing different sources with different kinds of values and using different mass calculations to arrive at a standardized list that allowed us to be as accurate as humanly possible. You can look at all of this in our source doc. As a result, this script was written with the tears of experts we drove crazy with our obsession for the best values they could live with. In this process, tons of stuff got cut and didn't make it into the final video. But luckily, we found a way to not waste all of it. We've created a lot of black hole merge, spanning the whole range from somewhat bonkers to more serious. This way, we get to explore a topic from different angles, and you get to continue having fun with black holes after the—
Okay, so I don't think they were, going too in-depth with the research, but I'm sure they looked through different academic papers. I just say that because a lot of people doing the actual work in the field on this stuff, they want to spread the actual communication of it, so they write media articles. So yeah, I'm sure these guys just were able to find information, collate it. I just also want to say, I feel like this guy should win some huge award in science communication, or this team, because these videos are truly amazing. Maybe even like there should be a thing like a Nobel Prize in science communication. I think that would be actually awesome. And I think it might be a thing in the future, because science communication is just as important as the science itself. Came up with this thing the other day. Science communication is to science what human senses are to the universe. So it's very important. But anyway, that'll do. Go check out this guy's videos. I'll catch you next time.